Pick up your phone right now. Seriously. Feel the weight of it, the smooth glass, the perfect symmetry. It took 400 engineers, 17 rare earth minerals extracted from 12 different countries, and semiconductor factories clean enough to qualify as operating rooms just to make that object in your hand. Now think about this. 12,000 years ago, a man sat down with a piece of antler bone, a river stone, and nothing else, and produced a blade so precise, so geometrically perfect, that modern metallurgists have studied it under electron microscopes and admitted they cannot reproduce the geometry using hand tools. Not that they haven't tried. They have, repeatedly. And they keep failing. That is not a story about primitive people. That is a story about a level of mastery so complete, so total, that it is essentially invisible to us now. And that invisibility is the most important thing I want you to understand today. If you knew everything your ancestors knew, you would be the most dangerous, most capable, most self-sufficient person in any room you walked into. Instead, we replaced that knowledge with supply chains. And the supply chains are starting to break. Stay with me, because by the end of this video, you will never look at a simple rock the same way again. Before we get into the list, subscribe right now if you haven't. This channel exists because people like you keep coming back for exactly this kind of content, and I don't want you to miss what's coming next. Number 25, the hand axe. Most people imagine something rough and shapeless when they picture a Stone Age hand axe, a rock with a chipped edge, something a child might make. The reality is so different, it genuinely shocks people the first time they hold a real one in a museum. Acheulean hand axes, produced between 7 million and 100 Zeusozoran years ago, are symmetrical along two axes simultaneously. Left to right mirror image. Front to back balance. The edges are worked in alternating patterns that distribute stress so precisely that the cutting edge resists chipping under load in the exact way that modern steel blades are engineered to resist. Researchers at the University of Exeter spent 3 years attempting to produce hand axes of equivalent quality using only period-accurate techniques and found that achieving Acheulean-level symmetry required a minimum of 5 years of daily practice. 5 years, just to make a rock sharp in the right way. The knowledge was so complex it had to be taught, practiced, and passed down across generations, or it simply ceased to exist. Number 24. Birch tar adhesive. Before glue existed in any form recognizable to us, ancient humans made it. Birch bark processed under specific heat conditions in an oxygen-limited environment produces a black adhesive tar with properties that genuinely puzzle material scientists. It bonds stone to wood. It is waterproof. It remains flexible in cold and does not become brittle in heat. And here is the thing that makes every researcher pause. Producing it requires maintaining a fire at exactly the right temperature, in exactly the right enclosure, for exactly the right duration, all without any instruments to measure any of those variables. Experiments in modern materials labs with temperature gauges and controlled environments routinely produce inferior tar compared to archaeological specimens. The ancient process encoded knowledge in the hands and the senses of the person doing it. That knowledge cannot be written down. It has to be felt. Number 23. Bone needles. 30,000 years ago in what is now Siberia, someone sat down and produced a needle from a bird bone so thin, so precisely tapered, with an eye so small and perfectly formed, that when researchers measured specimens from Denisova Cave, they found tolerances tighter than 1 millimeter. 1 millimeter, worked in bone, without magnification, without a vise, without any stabilizing tool we would recognize. The needle allowed the first fitted clothing in human history. Not draped animal skins. Fitted clothing with seams, with insulation layers, with specific thermal engineering built into garment construction. The needle did not just make people comfortable. It made them able to survive climates that would have been otherwise fatal. That single tool, smaller than your finger, is one of the primary reasons your ancestors were not wiped out by the last ice age. Number 22. Pressure flaking. The final stage of stone tool production was not striking. It was pressure. Using a pointed tool, often made from antler, Ancient knappers applied controlled pressure to the edge of a flint blade, removing tiny flakes with surgical precision to create edges so sharp they literally cut at the molecular level. Modern obsidian scalpels, used in some surgical procedures today because they produce cleaner incisions than steel, are less sharp than the best Solutrian pressure-flaked blades produced 20,000 years ago in what is now Spain and France. Think about that. The sharpest cutting edge ever produced by human hands was made before agriculture existed, before pottery, before the wheel, by someone sitting cross-legged on a dirt floor with a piece of antler and a rock. Number 21. Hafting. Attaching a stone blade to a wooden handle sounds simple until you try to do it in a way that survives actual use. The stone cannot be glued. It has to be mechanically secured in a way that absorbs shock without cracking the stone or loosening the join. Ancient hafting used a combination of birch tar adhesive, animal sinew wrapped in precise patterns, and carved wooden handles with slots and channels machined to tolerances tight enough to grip the stone without play. Experimental archaeology has shown that a well-hafted ancient spear point can withstand the force of penetrating thick animal hide repeatedly without coming loose. Poorly hafted reproductions fail on the first or second strike. The difference is entirely in knowledge that takes years to acquire and cannot be learned from a manual. Number 20. Bow drill fire starting. You have seen this in survival videos and thought it looked simple. It is not. The bow drill system requires wood species knowledge, moisture content understanding, geometry of the hearthboard notch, angle and speed of the drill, and downward pressure all calibrated simultaneously and intuitively for the specific conditions of that moment. Change the humidity, you adjust. Change the wood species, you adjust. The knowledge lives in the body, not in a set of instructions. Researchers tracking skill acquisition in primitive technology have found that producing fire reliably with a bow drill requires roughly 200 hours of practice before a person becomes consistent. 200 hours of a skill you will never use now because you have a lighter in your pocket that costs $1 and lasts a month. Number 19. Microlith production. Between 10 and 40,000 years ago, toolmakers began producing blades so small they require a magnifying glass to properly examine. Microliths, tiny geometric stone tools, sometimes only 1 centimeter in length, were hafted in rows along wooden or bone handles to create composite cutting tools that function the way a serrated blade functions today. Each microlith had to be produced identically to its neighbors, so the composite edge was consistent. We are talking about mass production of precision parts, by hand, in stone, tens of thousands of years before the Industrial Revolution invented the concept. Number 18. Bone and antler working. Stone is hard and brittle. Bone and antler are tough and flexible. Ancient craftsmen understood this distinction with a sophistication that materials scientists find remarkable. They knew which part of an antler was densest, which section of a bone had the right grain orientation for a specific purpose, how to use heat to make bone temporarily flexible for shaping, then allow it to cool into a permanently altered form. The thermal forming of bone is a technique that modern plastics manufacturing rediscovered independently in the 20th century. Your ancestors figured it out by observation and experiment roughly 50,000 years before a materials engineer in a laboratory filed a patent for the same basic principle. Leave a comment right now. Tell me which of these you actually knew about before today. I want to know what surprised you most, because the answers always tell me something about what we have lost. Number 17. Stone boiling. No metal containers, no fireproof pottery early in the record. How did ancient humans boil water or cook dense foods? They heated stones and fire until glowing, then used wooden tongs or woven carriers to transfer them directly into water-filled containers made of hide, bark, or woven fiber. A skilled practitioner could bring several gallons of water to a rolling boil and maintain it long enough to cook meat or render fat. The stones had to be the right type, because some stones crack explosively when rapidly heated and dropped in water, sending shrapnel in every direction. The knowledge of which stones were safe was not written anywhere. It was passed down, family to family, generation to generation, for tens of thousands of years. Number 16. Cordage and rope. Twist plant fiber one way with your right hand while twisting the assembled cord the opposite direction with your left, and the torque locks the structure together permanently without any knot or fastening. This is the principle behind every rope ever made, and it was understood and practiced by humans at least 40,000 years ago, based on impressions found in ancient clay. The plant knowledge required was immense. Which plants produced fibers of the right length and tensile strength, when to harvest them for maximum fiber quality, how to ret, process, and separate them. A rope that holds a load versus a rope that fails under load is determined entirely by knowledge of those variables. The wrong plant, harvested at the wrong time, processed incorrectly, produced cordage that snapped at the worst possible moment. Correct knowledge produced rope that could secure a shelter, haul an animal carcass, or rig a weapon for hunting. The rope was not the technology. The knowledge was the technology. Number 15. Ceramic firing without kilns. The first fired ceramics appear in the archaeological record around 29,000 years ago in what is now the Czech Republic. Fired not in a kiln, but in an open hearth, using a level of temperature management achieved by controlling the fuel, the airflow, and the positioning of the vessel that modern potters describe as almost impossible to replicate reliably without instruments. The ancient potters were managing heat with their eyes, their skin, and their accumulated knowledge of how specific types of wood burned at specific stages of drying. The same knowledge used by blacksmiths working iron in the 19th century, color reading the steel to judge temperature by eye, was being used by ceramic makers 25,000 years earlier. The tool was fire. The real technology was the human sensory system trained to levels of precision we have entirely outsourced to gauges and sensors. Number 14. Trapping systems. A deadfall trap is not a rock balanced on a stick. A properly engineered deadfall trap is a mechanical system with a trigger, a fulcrum, a striker, and a reset mechanism, all calibrated to the weight of the target animal, the material of the ground, and the likely approach angle of the animal based on behavioral observation. Ancient trappers built systems so mechanically sophisticated that researchers studying them for survival training have needed engineering backgrounds to fully analyze the mechanics. They required no metal parts, no springs, no manufactured components of any kind. Just wood, cordage, stone, and a level of mechanical intuition developed over lifetimes of observation. Subscribe now if you are not already. I am going to go deeper on some of these in dedicated videos and you will not want to miss them. Number 13. Tracking. This is not a tool in the physical sense, but it is a cognitive technology of such complexity that it has been seriously studied by evolutionary psychologists as a driver of human brain development. Expert trackers in traditional cultures can determine from a single set of footprints the species, size, sex, age, gait pattern, emotional state, speed, direction, time of passing, and health status of an animal. They can project future movement based on terrain, time of day, weather conditions, feeding patterns, and seasonal behavior. A study of San Bushman trackers in the Kalahari found that their ability to gather information from a track and reason about it forward and backward in time was indistinguishable in complexity from the kind of inferential reasoning tested in medical diagnosis and scientific analysis. The same cognitive machinery, trained on different data, with consequences, in their case, of starvation if they got it wrong. Number 12. Atlatl mechanics. The atlatl is a spear-throwing board that extends the effective length of the throwing arm, multiplying the speed of the projectile by a factor of up to 3. Simple in concept, brutally difficult in execution. The mechanical advantage only manifests if the flex of the board, the weight of the dart, the position of the spur, and the throwing motion of the user are all matched to each other with precision. Ancient atlatl makers understood flex mechanics, lever ratios, and projectile ballistics without any formal physics training. They understood them the way a master carpenter understands wood, not through equations, but through a combination of sensory feedback, accumulated experience, and transmitted knowledge so deep it lived in the body rather than the mind. Number 11. Watercraft construction. Dugout canoes require selecting the right tree species, felling it without steel axes, burning and scraping the interior to a wall thickness uniform enough to float without rolling, and shaping the hull to move efficiently through water. Each of those steps contains multitudes of sub-knowledge. The burning technique alone varies by wood species, ambient humidity, and desired final wall thickness in ways that require hundreds of hours of practice to internalize. Bark canoes, as made by multiple indigenous groups across North America, were even more sophisticated, requiring knowledge of bark harvesting seasons, folding techniques, waterproofing materials, and structural reinforcement that allowed a vessel weighing under 40 pounds to carry 5 people safely across open water in conditions that would threaten a modern recreational kayak. Number 10. Pigment preparation and application. Cave paintings that have survived for 40,000 years were not made with paint from a tube. Ochre and other mineral pigments were processed by grinding, mixing with binding agents including animal fat, plant oils, and blood, and applied using tools ranging from fingers and sticks to what appear to be early brushes and even blowtube atomizers made from hollow bone. The binding chemistry had to work. A pigment that did not bond to the rock surface properly would fall off within years. 40,000 years later, those images are still there. Whatever binding ratio those painters used, it was correct enough to outlast every material we have manufactured in the modern era. We are still experimenting with paint chemistry. They already solved it. Number 9. Basket weaving with structural integrity. A woven basket is not decoration. Properly constructed, a basket can carry hundreds of pounds of grain or water without failing. The structural strength comes from the geometry of the weave pattern, the material properties of the fibers selected, and the tension management during construction, which requires both hands to be doing different things simultaneously, while the third variable, the emerging shape of the basket, is managed by eye and feel. Research into traditional basket weaving has found that producing a basket capable of carrying significant weight requires not just the weaving skill, but a specific botanical knowledge of fiber selection, harvesting timing, and preparation that takes years to transmit. The basket was the deliverable. The knowledge tree required to make a functional one was enormous. Number 8. Obsidian sourcing and trade networks. Obsidian, the volcanic glass prized for its exceptional cutting edge, was traded across distances that challenge our assumptions about ancient mobility and social organization. Obsidian from sources in what is now Turkey has been found in archaeological sites across the entire Middle East. Obsidian from specific volcanic sources in the American Southwest appears in sites hundreds of miles from any known source. Ancient people tracked not just where obsidian came from, but which specific volcanic flow it came from. Because different flows produced glass with different flaking properties, they were managing a supply chain with quality control standards, without writing, without maps, without any of the organizational infrastructure we consider necessary for supply chain management. The technology was social and cognitive, not material. Number 7. Animal behavior knowledge for hunting. A modern hunter with a rifle and GPS struggles to find a specific animal. An ancient hunter with a spear and an atlatl could locate, approach, and successfully take an animal because they knew that animals' behavioral patterns, habitat preferences, daily movement rhythms, seasonal routes, social structure, stress responses, and escape behaviors well enough to anticipate and intercept. The knowledge base required was equivalent in volume and complexity to a graduate-level course in animal behavioral ecology. The consequence of ignorance was not a missed opportunity. It was starvation for the people depending on the hunter. When survival depends absolutely on knowledge, knowledge reaches levels of precision we have never needed since the invention of the grocery store. Drop your comment down below right now. Tell me which skill surprises you the most, because something tells me it is not the ones you expected. Number 6. Sinew preparation and use. Dried sinew from large animals is one of the highest tensile strength natural materials available to a craftsman working without metal or synthetic fibers. Dried and split correctly, it can be used as thread, as bowstring, as hafting material, as structural reinforcement for wooden tools. But the preparation is critical. The sinew must be dried in a specific way to avoid brittleness, twisted under tension at a specific moisture content, stored in conditions that maintain its flexibility without allowing it to degrade. Ancient craftspeople knew the difference between sinew from different muscle groups of the same animal because they had different tensile properties and served different purposes. That is material science, operating 60,000 years before anyone invented the concept. Number 5. Tanning hides without synthetic chemicals. Brain tanning, the process used by indigenous peoples across multiple continents independently, uses the emulsified brain of the animal being skinned to tan its own hide. The chemistry works because the lecithins in brain matter permanently soften the collagen fibers of the hide without making them rigid the way vegetable tanning does. The result is a leather so soft, so flexible, and so durable that professional leather workers handling brain-tanned hides for the first time routinely assume they are handling a synthetic material. Producing it requires scraping the hide to exact thickness, applying the brain solution at the right temperature, working the hide continuously for hours as it dries to prevent stiffening, and smoking it at the end to make it waterproof. Doing any one of those steps incorrectly produces an inferior product. Knowing all of them well enough to produce consistently beautiful brain-tanned leather required years of apprenticeship under someone who had years of apprenticeship under someone else. That chain of transmission, that unbroken line of hands-on knowledge moving from human to human across thousands of years, was what made the technology work. When the chain broke, the technology did not survive the break. Number 4. Celestial navigation and seasonal calendaring. Without clocks, without written calendars, without any fixed reference point in the landscape other than the sky, ancient peoples tracked time with a precision that determined whether their communities survived. The migrations of game animals had to be anticipated. Planting timing for early agricultural experiments had to be accurate to within days. The solstices and equinoxes that structured the ritual and practical calendar of every ancient culture we know of were not approximations. They were precise observations refined over generations. Stonehenge is the famous example, but it is one of thousands of structures worldwide built with solar alignment, accurate enough to mark the solstice within a day or two. The people who built those structures did not have surveying equipment. They had accumulated observational knowledge of how light moved across specific landscapes over decades of careful watching, and they embedded that knowledge in stone. Number 3. Plant medicine knowledge. Before pharmaceutical chemistry existed, an enormous body of pharmacological knowledge existed inside human communities. Not guesswork. Accumulated clinical observation refined across hundreds of generations. Aspirin is derived from willow bark. Digitalis, the heart medication, from foxglove. Quinine from cinchona bark. Morphine from poppy. The pharmaceutical industry spent the 20th century isolating active compounds from plants that traditional healers had been using correctly for thousands of years without knowing what the active compound was. They knew the plant worked for specific conditions. They knew the dose ranges. They knew the contraindications. They knew which preparations enhanced efficacy and which produced dangerous side effects. Ethnobotanists studying the last remaining holders of traditional plant knowledge have documented pharmacological sophistication that consistently outperforms anything that could plausibly result from random trial and error. This was systematic knowledge, managed and transmitted with as much rigor as it could be without writing. Number 2. Controlled burning and landscape management. Australia's indigenous peoples managed a continent using fire, not randomly, not destructively, specifically, seasonally, and with an understanding of ecological succession so sophisticated that European settlers arriving in the 18th century assumed the landscapes they saw were natural. They were not. They were managed. Strategic burning cleared undergrowth, encouraged specific plant species that attracted game, prevented catastrophic wildfire by reducing fuel loads, and maintained the mosaic of habitat types that supported maximum biological diversity. When that management stopped after colonization, the landscape began deteriorating almost immediately, with catastrophic wildfire frequency increasing and biodiversity declining. Modern conservation ecologists spent decades relearning what indigenous Australian land managers had known for 60,000 years and never stopped practicing until they were stopped. And now, the one that archaeologists, materials scientists, and experimental researchers keep coming back to. The one that keeps generating new papers, new experiments, and new admissions of how little we actually understand. The one that started this conversation about ancient tools modern people cannot recreate. Number 1. The Inca stone masonry without mortar. Stand in front of the walls at Sacsayhuaman in Peru. Look at the stones. Some of them weigh over 100 tons. They were cut from quarries miles away, transported without wheels, without steel tools, without draft animals capable of that load, and fitted together in interlocking polygonal patterns so precise that in 400 years of Andean seismic activity, including multiple major earthquakes that have destroyed modern concrete structures around them, these walls have not shifted. The mortar-free joints have not opened. The stones have not moved. Engineers studying the walls have concluded that the fitting geometry itself is part of the seismic resistance. The irregular polygonal shapes distribute seismic energy in ways that prevent resonant frequency buildup of the type that destroys regular rectangular structures. That is not intuitive masonry. That is applied structural engineering. Without structural engineering as a field, without mathematics as we define it, without instruments, without anything we would recognize as formal knowledge transmission, the people who built those walls knew something about stone, seismic force, geometric load distribution, and large-scale logistics that we genuinely, honestly, provably do not fully understand today. Not because we lack intelligence, because we lack the specific knowledge base that lived in them and died when the culture that carried it was destroyed. Spanish colonial conquest did not just kill people. It terminated a line of knowledge transmission that had been running, unbroken, for centuries. Those walls are what remains. The knowledge that built them is gone. We can study the walls. We can measure them, scan them, model them with supercomputers. We cannot reproduce them. We think of knowledge as something that accumulates over time, that we know more now than people knew then. And in many ways that is true. But knowledge also disappears. Entire domains of understanding, honed over thousands of years of necessity, vanished when the conditions that created and sustained them changed. We do not know how to knap an Acheulean hand axe. We cannot reliably produce birch tar of ancient quality. We cannot brain tan a hide the way a Sioux grandmother could. We cannot read a track the way a San Bushman reads a track. We cannot fit a stone wall to earthquake-resistant tolerances without equipment. The people who could do all of those things were not smarter than you. They were not superhuman. They were trained in knowledge systems so demanding, so deep, so physically embodied that they took a lifetime to acquire and could not survive even one broken generation of transmission. That is what we lost. Not intelligence. Knowledge. The hardest kind of knowledge to get back. Because it does not live in books. It lives in hands. So here is the challenge. Find one thing from this list and go learn it. Not watch a video about it. Actually learn it. Find someone who knows it, or find the raw material and start the process of figuring it out. Because the supply chains holding your life together are not as permanent as they look. And somewhere in your hands is the same capacity those ancient craftspeople had. It is just waiting for the right pressure to reveal it. Leave a comment right now. Which of these are you going to try first? I read every single comment, and I want to know.